We're going to start lesson 5.2, which is derivatives of a general exponential function, y equals b to the x. We've seen this function in grade 11U, and we're going to just keep on going with it when we're taking derivatives. It's going to be kind of interesting. We can actually see what the functions look like for the standard b to the x. So if we look at it, we can see that there's an asymptote, which it's starting at the asymptote, and it's going up and up and up. It goes to a y-intercept for the standard one, which will be 1, and it keeps on going up exponentially. If the value of b is less than 1, then it's going to go down to the right instead of up to the right. Let's do a couple of limits. So for example 1, it says, use the graph of the exponential function to evaluate each of the limit. So in this case here, we have the limit of 2 to the exponent x. So if we think about it logically, if I were to put in a value, let's say for example 2 for the exponent, it will be 2 to the exponent 2, which is 4. If it's 3, it's going to be 8. If it's 4, it's going to be 16, and it doubles each time. So as the value of x gets really, really, really large, what's going to happen is our limit is going to be really, really, really large. And we can just call it positive infinity. When we deal with, for example, b, it says it's approaching negative infinity, i.e. the value of x is getting really, really small. What's going to happen is we're going to have the exact same values that we had for 2 to the exponent x, but it's going to be 1 over. So if we keep that in mind, the denominator is going to get really, really, really big. Our numerator stays as 1, so what's going to happen in essence is this is going to approach 0. The same premise is going to apply for this one here. In this case here, we have 0.2, which is, in this case here, b is less than 1, and we're putting x to be a really large number, so in this case here, it's going to approach 0. And the opposite is going to be true for this one here. It's going to be 1 over 0.2. 0.2 is, let's say, 2 over 10, so it's going to be 2. So if we take its reciprocal, it's going to be 10 over 2. And what's going to happen is if we put a big exponent for that, it's going to get really, really large. So it's going to be positive infinity. We have to commit to memory what the derivative of an exponential function with base b is. So if we look at it, we know that the derivative of b to the x is going to be ln of b times b to the x. There's the proof there. You can look it over at your leisure. And the next thing we have to look at, the most importantly, is equation number 2, where it says we're going to take the base of b with an exponential function that is actually a function. So we have to use the chain rule. Okay, so when we're using the chain rule, this is pretty much the form we have to look at. Let's do an example. So in this case here, this is different than what we're used to, for example, number 2a, because our base in this case here is a number. So if it's a number to some kind of exponent, we treat it differently than if it's a variable to some kind of exponent. So if we want to do this one here, the first one is, according to our formula, 3 to the exponent x, derivative is going to be the ln of the base times the actual function itself. And we can write that whichever way you want. Doesn't make a difference in this case here, right? For the next one, we have x squared times 2 to the exponent x. So that means there's the product rule there that I have to use, and there's going to be a little bit of the chain rule because we have 2 to the x, which is going to change the form up a little bit. So if we're using the product rule, derivative of x squared is going to be 2 to the x, times we have 2 to the exponent x, plus we have our x squared, times derivative of 2 to the exponent x, which is going to be ln of 2, times 2 to the x. And we can simplify this by factoring out whatever we can. So in this case here, I can factor out an x, and I can factor out a 2 to the x. So if we do that, let's see what it looks like. So I said we're going to factor out an x, and we're going to factor out 2 to the x. What's left on the first one? What's left on the first one is going to be the 2. We have the plus. We have an x left over, ln of 2. That would be the factor simplified version. For the next one, we have a function within a function. So we know already when we use the chain rule. So our derivative here is, if we treat it as a whole entire function, we have to drop the 3. Reduce the exponent 3 to 2 by reducing it by 1, times we have to take the derivative of what's inside the bracket. So we have 4 to the x, which is going to be the ln of 4, times 4 to the x. And it's probably a good idea to put brackets around everything, but I'm not going to. Plus derivative of x to the exponent 4, which is 4x to the exponent 3. I'm going to see if I can simplify something. It's kind of hard. We may have to expand it, collect like terms, see if we can factor it a little bit more, make it look a little more pretty. I'm not going to worry about it. Let's try example number 3. Example number 3 says, use the chain rule to differentiate. And the big difference here is, first of all, we have a negative in the exponent, plus we have a function in the exponent. So we have to be careful about that. So when I'm taking derivative of an exponential that has a number as the base, it's going to be the ln of the number base times the base itself, to the exponent itself, times derivative of the exponent. So derivative of the exponent would be this part over here, the highlight. So that means when I drop the 3, so it's going to be negative 3x squared. And then we'd have to rearrange this to something that, follows the rules and everything else. All I'm going to do for this one is I'm going to bring the 3x squared to the front, negative 3x squared. And then I'm going to put the ln of 2, and then I'm going to have times the 2, the negative x to the exponent 3. That may or may not be the way the solution at the back of the book express the answer, but I'll accept it. For the next one, this is a good test type question because it has a lot going on there. Now we have e's in there as well. That's from 5.1. I have to remember that it's going to be the ln of the base times 10 to the exponent of e, and I can't see what that says, kind of small, e to the x minus x squared, times, now I have to take the derivative of that, right? So remember that we have e to the x minus x squared all to the exponent 1/2. So I'm going to drop the 1/2, there it is. I'm going to reduce the exponent by 1, so we have e to the x minus x squared to negative 1/2. And then I have to take the derivative of what's inside the brackets as well. I didn't highlight, there it is. So that means I got to take the derivative of e to the x, which e to the x is basically just e to the x. And then take the derivative of negative x squared, which is minus 2x. We can clean this up, right? So let's see what goes on the top. Well, we have the ln of 10. Oops, I said ln of 10. Put brackets around ln of 10, right? Moving further along, we're going to have e to the x minus 2x. And we also have the 10 and the root of e to the x minus x squared. And on the denominator, we have the 2, which did not get canceled out. And we have the root, which is e to the x minus x squared, and the square root. I'm looking to see if I can cancel anything out. Doesn't look like I can, so I think we're golden. Excuse me. For the next question, it's saying find the equation of the tangent line of the graph, which f of x is equal to x times 2 to the negative x at 0, 0. So the first thing I'm going to focus on is when I'm finding the equation of the tangent line, that means I have to do a derivative. So let's do the derivative. We're going to have f prime of x, and that's going to be equal to derivative of the x, which is 1, right? 1 times the bracket to the negative x. And then it's a product, so plus, I'm going to have my x times derivative of 2 to negative x, which is equal to times ln of the base, right, times itself, times the derivative of the exponent, so it's going to be negative 1. we're going to set that equal to 0. I'm not sure if there's any value of cleaning this up. We can just put f prime, we want to say when it's equal to 0. So that means we're going to have 2 to the negative 0 plus 0, and everything else goes to 0. All right, I can still put ln of 2 to the negative 0. If you want, you can change the sign. We know that this all goes to 0. And 2 to the negative 0 is the same thing as saying 2 to the exponent 0. Anything to the exponent 0 is equal to 1. Therefore, f prime of 0 is equal to 1, which I already did. So it's going to write, therefore, it's going to be 0 and 1. So this really here is my slope. Let me take that out, sorry. Sorry if I confused you. Basically, this is going to be my slope, m, and we have a choice of how we want to do this, right? We can say that, well, when we come up with the equation, we can use this form, or we can use the, the y is equal to mx plus b, it's the same thing. So in this case here, I know that, if I scroll down here a little bit, this is my x1, this is my y1. So if I replace it, we're going to have y minus my y1, which is 0. Our slope we calculate, which is 1. I'm sorry, I'm going to get rid of that 2 there. There's no 2 there. Sorry. And we're going to have our x minus our x1. Our x1 is going to be 0 again. So if we clean this up, we have y is equal to x. And that'll be our answer. For example 5, it's asking to find the local extrema. So lots of ways of doing this. Let's see what this comes out for us. When we find the local extrema, we have to find its derivative. So to find its derivative, again, I'm going to use product and chain. So we're going to take the derivative of x squared, which is 2x. So it's the derivative first times the second, which is going to be e to the negative x squared, plus we're going to have our x squared, which is the first, times derivative of the second, which is going to be the, so now we're doing with e's, right? So it's not going to be ln, right? So it's going to be times e to the negative x squared times derivative of the exponent, right? It's going to be times negative 2x. It may help to put brackets around everything. I'm not sure if you can see it. If you can't see it, put brackets and it should help you out. Now I'm going to try and factor out the greatest common factor, right? Because we're not looking at one specific point. And we can see that we have in both of them a 2x. In both of them we have an e to the negative x squared. So, oops, highlight the second part and come out. So that means I'm going to take out 2x, e to the negative x squared. And if I do that, and I have 1 minus, just making sure I don't make a mistake here, x squared. Okay, now we know that f prime of x is equal to 0 when we have 0 is equal to 2x e to negative x squared times 1 minus x squared. We're going to set this equal to 0. So the only time that's equal to 0 is when x is equal to 0. And here, I'm going to set that equal to 0. I'll just, you know what, I won't skip any steps. Let's go back a little bit. So we're going to have 0 is equal to 2x e to the negative x squared. And the exponent never makes it go to 0. So the only thing that's going to make it go to 0 is the x beside the 2. Oops, sorry. So we have x equals 0 for that one there. And if I do f of 0, that's going to equal 0. So therefore 0, 0. The other one we have is when we have 1 minus x squared is equal to 0, or x squared is equal to 1, or x is equal to plus or minus 1 when I take the square root of both sides. Okay, so what I'm going to do, oops, I pick a pen, f of negative 1. So it's going to be 1 times e to the negative 1, which f of negative 1 is going to be 1 over e. And if I do f of 1, it's going to be 1 times e to the negative 1, which f of 1 is going to equal to 1 over e. So the next thing I'm going to do is create a table and see if this works. I did a table before, I hope that's enough. There it is. And we're going to fill this in. So what we're going to have is our x. It doesn't matter in the order, so I'm just going to leave it like this so we can play around with the order a little bit. And our first critical point was negative 1. Our second critical point was 0. Our third was 1. And if I plug in a value that's less than 1 into our function, we're going to see that it's going to be a positive, which means it's going to be increasing to our critical point. Our critical point is negative 1, and we calculate that value to be 1 over e. And then we calculated the second critical point to be 0, 0. Might as well fill in all the critical points. And the last critical point, again, was 1. So if I plug in a value into our table that's between negative 1 and 0, let's say negative 0.5, I'm going to square it becomes a positive. Put a negative, it's going to be a positive. Let's double check, sorry. Put in a negative 0.5. It's going to be a negative, and it should be going down. And if I plug in a value between 0 and 1, plug it in there, it's be 0.5 squared, positive, times that, it's going to be a small positive, so it's going to be a positive going up. If I plug in a value greater than 1.1, greater than 1 into my derivative function, just so that it's going to be negative. That means decreasing for my function. So let's summarize what we've done. So from the chart, we can see that we have a local max at negative 1 and 1 over e, and 1 and 1 over e. And we have a local min at 0, 0. We don't care about the absolute values, we just care about, in this case here, the extrema for those 3 critical points. Find the points of inflection for the function. So when we're doing points of inflection, that means we have to do a double derivative. So let's do this. Our first derivative is basically, well, it's going to be e to a negative x squared times derivative of the exponent, which would be negative 2x. Right, if I clean this up, negative 2x e to the negative x squared. Our second derivative is going to be derivative, now it's a product chain, right? Derivative of negative 2x, which is going to be negative 2, times the second, plus, or plus minus, right, really, because it's negative 2. So minus 2x times the derivative of e to negative x squared times e to negative x squared times the derivative of the exponent will be negative 2x. We're going to see what we can factor out. I can factor out a negative 2. I'm going to factor out e to negative x, so there's my negative 2. And there's my e to negative x squared. So we're going to say f double prime of x is equal to negative 2 e to negative x squared. And when I do that, excuse me, I have 1 minus, well, it's actually minus negative 2, so plus 2x squared. Just checking my signs. That's a negative, so the negative comes out. becomes positive. Sorry, that means that this sign just comes out to be negative. All right, f double prime is what we care about. Is equal to 0 when we have negative 2e to the negative x squared equal to 0. And when we have 1 minus 2x squared is equal to 0. In the first case, no matter what value I plug in for the exponential for x, it's always going to be, there's never going to be a value that goes to 0. And for the second one, this is going to be when we have 2x squared is equal to 1, or x squared is equal to 1/2, or x is equal to plus or minus root 2 over 2. Skipped a couple of steps there, right? It's really the same thing as saying the root of plus or minus 1 over root 2. Then I rationalized it. I'm going to have to come up with a table so we can actually see if it actually works out. So if I do this, again, we may have to add more if we need some more. And we have 1 for the function. Then we have 2 points that we're testing around, so it means I need 2 plus 3, so I need 5 in the middle. So they're not going to be very big. 1, 2, 3, 4, 5. I think I did an extra one there, but it's okay. If I did an extra, just leave it alone. I'd rather have an extra one than not enough. So this is going to be my x. This is going to be my f of x. This is going to be my f double prime of x. So our first point that we're going to test around is going to be negative root 2 over 2. The second one we're going to test around is root 2 over 2, positive. So when I plug in a value that's less than negative root 2 over 2 into the function, we can see that it's going to be a positive. If it's a positive, it's going to be concave up. And we know that this is going to be 0. I might as well put those there, right? Because that's what we solved for. And what I didn't solve for was what happens at f of those values. So if I do f of root 2 over 2, that's going to give me 1 over root of e. And if I do f of root 2 over 2 negative, that's also going to give me 1 over root e. So it means that over here, oops, sorry. Come on. And this will be 1 over the root of e. And this will be 1 over the root of e. And if I plug in a value between the two critical points, like for example 0, into my second derivative function, anything to the exponent of 0 is 1, so I have 2. We're going to have a negative value, so it's going to be concave down. And if I do 1 after, so if I do something greater than that, let's say, I don't know, 2. I'm just doing it in my head. It's going to be positive, so it's going to be concave up. So therefore, we can say that our inflection points at x equals plus or minus root 2 over 2 and 1 over root e. So let me just take out the x. I think there's one last example. Find the global extreme of 4. And in this case here, we have the domain which is bound. So we have to see how that comes into play. So the first thing I have to do is take its derivative. Derivative of 3dx is 3x squared times 10 to the exponent x. So times 10 to the exponent negative x, plus x to the exponent 3 times the ln of 10 times negative 1. Oops, I forgot something. So ln of 10 times 10 to the exponent negative x times negative 1. if we simplify this, can we simplify this? I can take out an x squared, 10 to the negative x. So there's an x squared, 10 to the negative x. There's going to be a sign change in there. So if we do f prime of x, excuse me, we have our x squared dissecond factor out times 10 to the exponent negative x. And what's left? On the first part, we have 3. On the second part, we have x ln of 10. Then I forgot to account for the negative, so I got to change the positive in between into a negative. And we know that f prime of x is equal to 0 when we have x squared times 10 to the exponent negative x equal to 0, and 3 minus x ln of 10 equal to 0. For the first one, doesn't matter what I put for the exponent, it's never going to make it a 0. So that means the only thing that's going to make it a 0 is the x squared, so x equals 0. If I were to do f of 0, it's going to also be 0 because we have x to the exponent 3 makes it 0. In the second one, I've got to solve for x, so it means I'm going to bring the 3 is equal to x ln of 10, or x is equal to 3 over ln of 10. And for you decimal lovers, it's approximately equal to, grab my calculator, 1.303. If I do f of 3 over ln of 10, and I'm putting that into the calculator, eventually I think, 3 over the ln of 10, all to the exponent 3, times 10 to exponent negative 3 over ln of 10. I'm going to get approximately 0.110. So if I'm trying to figure out if that's a max or min over 1 and 2, I got to test what the value of 1 and 2 is. So what I'm going to do is I'm going to put into my calculator f of 1. So if I make x equal to 1, that means we have 1 to the exponent 3, which is 1, times 10 to the exponent negative 1, which is going to be 0.1. And if I do f of 2, we have 248 times 10 to the exponent negative 2, which means 8 over 100. It means f of 2 is equal to 0.08. So in this case here, it's going to be 1 and 0.1. In this case here, it's going to be 2 and 0.08. So we can clearly see that that value there is higher than the 0.1. So therefore, the global maximum point is at, I'm going to say approximately 1.303. If we want to, we can actually be more exact. Let's do more exact. Should we do more exact? It's kind of hard when you have the one's decimal, so no. And we said it was 0.110 to 3 decimal place. And then the global minimum, the global min point is at, and the minimum, the lowest point was the 0.00. It's bounded there, so the lowest point would be the 2 and the 0.08. And that's it for today.